Hello and welcome to this next session on our exploration of spectrophotometry. We need to continue our discussion on waves, and we need to understand what waves are before we can truly understand what processes exist in our spectrophotometric experiments. So let's get going. So spectrometric methods are a large group of analytical methods that are based on atomic and molecular spectroscopy. Spectroscopy deals with the interactions of various types of radiation, mainly electromagnetic radiation, with matter. Spectrometry and spectrometric methods refer to the measurement of the intensity of radiation with a photoelectric transducer or other types of electronic device. Electromagnetic radiation is energy with wave character. It can be characterized by using wavelength, frequency, velocity, and amplitude. So these are all characteristics of a wave. So here is a common sine wave. It starts at the origin and it passes through time and space. So we have here, it oscillates around a central fixed position here, which is known as the axis of propagation. So there are distances between the peaks, which are these parts, which are the maximum positive amplitude, which the amplitude being the distance, along this vector from the propagation axis to the peak at the top in the positive region or the trough in the negative region. Positive and negative are rather arbitrary in this sense. Wavelength then is the distance in like centimeters, meters, nanometers, whatever it happens to be, between two successive peaks or two successive troughs. The amplitude is the length of the electric vector at a maximum in the wave. So the wave, this is the wave, the red line, the maximum is here. The period is the time in seconds required for the passage of successive maxima or minima through a fixed point in space. The frequency f is the number of oscillations of the field that occur per second and is equal to 1 over p, the period. And this is given the unit of reciprocal seconds or hertz. Reciprocal seconds can also be read as per second. And so this is the number of oscillations. So a complete oscillation of the wave is whenever it comes back to the starting point again. So it starts here, it goes through, and that is one wave. That would be the time that it takes for that to pass through this point. So say we're propagating like this, the time it takes for one complete wave to pass through the same point is going to be the period. And the number of those periods per second is the frequency. So the wavelength then is the linear distance between any two equivalent points on successive waves, successive maxima or minima. It actually doesn't even need to be the maxima or minima. It just needs to be the same point on the wave. And it's literally a distance. Then wave speed is given by this equation here, where velocity is equal to the frequency times the wavelength. So all of these things, this light, can be described as electromagnetic radiation. So electromagnetic radiation requires no supporting medium for its transmission and can pass through a vacuum. So that's why we have this astronaut in space right here. So here is a vacuum. They're protected from the vacuum by their spacesuit, but the electromagnetic radiation can pass through here, and that's why we can actually see this person. Now, this astronaut can be seen because the electromagnetic radiation and light from the sun are going to be reflected off of their surface. So electromagnetic radiation is a stream of discrete particles or wave packets of energy called photons. And so most of what we'll deal with today is going to be regarding photons. So photon energy is proportional to the frequency of the radiation. So we already talked about frequency as being the number of periods of that wave per second. So here we have the transmission of radiation. So we have an amplitude, a And we have a distance along the x-axis. We have it passing through air, we have it passing through glass, we have it passing through air. So even though this electromagnetic radiation does not explicitly require a supporting medium, the presence of a supporting medium is not a hindrance and does not stop it. It can still pass through a supporting medium. Air is a supporting medium. The sound through which my voice is carried, or my voice is carried as sound waves through the air by the particles in the air. If I was in a vacuum, you would not be able to hear me, and I would not be able to breathe. The glass would pass, it can also pass through glass. It just depends on the medium and the effect that these media have on the electromagnetic radiation is that they change the wavelength. They do not change the frequency, but they do change the wavelength, such that in less dense medium, or well, it's easiest to compare it between different types of medium. So in less dense medium, if it moves into more dense medium, so for example, going from the air to the glass, what we see and what we observe is that the wavelength is compressed. So the wavelength goes from a long wavelength, say 400 nanometers, to a much shorter wavelength, say 160 nanometers. And then from the glass, it passes through the air again, and it will recover its wavelength. So the wavelength will go back. There will be no lingering effect caused by the glass on the wavelength. The wavelength will return to its original value, assuming that the density of that media is the same as before. So the frequency remains the same, but velocity and wavelength change. The velocity changes because the wavelength changes. Remember, the velocity is equal to wavelength times frequency. So the velocity of propagation is equal to the wavelength times the frequency. So in vacuum, the velocity of radiation is independent of wavelength and given by the symbol c, where c is the wavelength times the or wavelength times the frequency, which is 3.00 times 10 to the minus 8 meters per second, sometimes given as 2.998. And then it can also be written, of course, in different units. You can write it in centimeters per second as well. Now, the wave number given as the reciprocal of the wavelength in centimeters is given as centimeters to the minus 1. Wave number is a typical way of describing the spectra in things like infrared spectroscopy. Not so much in terms of absorption spectroscopy, but definitely in infrared spectroscopy. The electromagnetic spectrum then, so the electromagnetic spectrum encompasses an enormous range of wavelengths and frequencies. Spectroscopic methods are classified according to the wavelengths or frequencies that are important for analytical purpose. Here are the regions of the electromagnetic spectrum as it pertains to what we will be studying here in this topic. So we have a bunch of regions here, 7 in total, which are labeled gamma ray, X-ray, ultraviolet, visible, infrared, microwave, and radio waves, and they go from high energy to lowest energy here. And so the energy of the waves, as we will see later when we encounter Planck's relationship, can be related to the frequency and the wavelength and the wave number. All of these can be interrelated, and that's why we're given each one of these 3 scales. Now, the wavelength here of the high energy waves, such as gamma rays and X-rays, is given as the short wavelengths. So very short wavelengths, 10 to the minus 3, almost on the sort of same length scale as things like DNA. And it passes through like ultraviolet, which is sort of on the length scale of cells, visible then, which is not really on the length scales of most of biological tissue, infrared, microwave, radio waves far beyond the length of most of our biological tissues. And so for this reason, it is, it's one of the reasons why things like gamma rays and X-rays and things like that can be dangerous. So gamma rays are particularly dangerous because they are on the same length scale as DNA and things like that, and so can cause irreversible damage. X-rays tend to be kind of in between, so they're like they're smaller than a cell, but yet they're bigger than like molecules and things like that. So short-term exposure to X-rays is generally seen as being okay. That's why it's okay to get the odd X-ray if you need it for medical reasons or whatever, but long-term exposure is not recommended. Ultraviolet, then the light is on the same wavelength scale. It's got the same sort of, the wavelength is about the same distance as a biological tissue cell. And so that's why it can be dangerous to be exposed to too much ultraviolet radiation. But again, short-term exposure is generally seen as being okay, but not anything, not at high intensity. And then things like radio waves, they're generally seen as being completely safe because the length scales here are on like tens of meters, things like that. So they're far, far larger than biological tissue. And so it means that they can't interact with biological tissue. So by and large, can't really do anything. So they can't interact, they can't do anything. So radio waves are used like for, transporting music whenever you're sitting in a car, maybe listening to the radio, or transporting information such as like through Wi-Fi or through TV and stuff like that. So regions are based on the methods used to generate and detect the various kinds of radiation. And the portion of the spectrum visible to the human eye is tiny compared to the other spectral regions. So you can see the other spectral regions are massive, but visible is very, very small. So here is some more detailed information on these. So we have the energy. So we didn't have energy on the last one. We just had number lines. But now we have energy in electron volts and also in kilocalories per mole. We have wave number, wavelength, frequency. We have the different types of radiation here, gamma ray through to radio, of course. Type of spectroscopy that we use here. Generally, the type of spectroscopy is named after the region. Although generally the version of that changes. So like in gamma rays, we typically use emission. X-rays, you can use absorption and actually emission. UV is absorption, IR is absorption, microwave is absorption, and radio waves are used in nuclear magnetic resonance, which is called NMR, which is a very important thing in organic chemistry. And then the quantum transitions are over here. So with nuclear quantum transitions in the case of gamma rays and X-rays, that's why it's kind of dangerous because it interacts with the nucleus. X-rays are electrons, inner shell electrons, so the ones close to the nucleus. UV is outer shell electrons, so like the valence electrons, the HOMO and LUMO electrons. Infrared is molecular vibrations, molecular rotations, which also go into the microwave region. And then magnetically induced spin states are those seen in some forms of microwave ray absorption and in all forms of NMR. So I told you before that we were able to find a relationship between frequency, wavelength, and energy. And this is it. This is Planck's equation or Planck's relationship. And so this is the relationship between frequency of light or electromagnetic radiation and energy E. And so E is equal to Planck's constant times the frequency, where H is Planck's constant. And so that's 6.6 times 10 to the minus 27 erg per sec. And then that can be converted into joule secs. So in the vacuum, the velocity of light is equal to C is equal to frequency times the wavelength, 3.3 times 10 to the 10 centimeters per second, which can be rearranged to give it in terms of frequency as speed of light over lambda. And then that can be substituted into our original Planck's equation, this one. So we get E is equal to H times C over lambda, which is equal to HC V, where the V is equal to the wave number, which is 1 over lambda. And so this means that energy is directly proportional to wave number. And so wave number, frequency, and wavelength can all be interrelated according to this relationship, Planck's relationship or Planck's equation. And a very, very important equation, this one and this form here as well. They are very, very important and are worth remembering. So waves, so one of the important things about waves is, and one of the reasons why they're useful in carrying information, is that they can be added and subtracted. We call it constructive and destructive interference, but it's effectively just adding and subtracting. So if we have two plane polarized waves, that means they're pointing in the same direction, and they overlap in space, we will get a resulting electromagnetic disturbance as an algebraic sum of the two waves. So we have constructive and we have destructive interference. The constructive interference causes the increase in the amplitude. So you can see here the amplitude is around about 2. If we combine these together, which are perfectly in sync or in phase, then it doubles. And so it goes from 2 to 4. Destructive interference is whenever they're out of phase, so they don't line up. And if they're perfectly out of phase, then we get destructive interference. And this is one of the ways in which things like noise canceling headphones work, by actively producing waves in that will interact destructively with the noise outside, which is why you need to charge them and stuff like that. They don't just work without power, because they need some energy to produce the waves. So optical interference is the interaction of two or more light waves yielding an irradiance that is not equal to the sum of the irradiances. Constructive interference is they have identical frequencies and they're added together. Destructive interferences have identical frequencies, but they are going to be destroyed. So the benefit of this is that if they only partially overlap, we get both constructive and destructive interference, and it creates something called periodicity or beat. And so this sort of wave structure here comes from the superposition of these two waves on top of each other. So superposition just basically means they're coincident, or like basically they come together. And the combination of these produces this, which is kind of like a beat-like structure. So we've got a high amplitude, low amplitude, high amplitude, low amplitude, like the beat of a music piece or something like that. But there are mathematical techniques, and this is the power of this, which can deconvolve this into these. And so we can get information for the various different parts. So we can convert this, which is the combination, which is what would be observed or heard by us in our ears, but it can be deconvolved into this and this. And so that can allow us to extract important information out of that and allow us to use that information to like put text on a screen, or to access the internet, or various other things. And get well, the basic use for this in science is like, we also use this in Fourier transform infrared spectroscopy, which unfortunately we won't cover in this course, but it uses this idea of superposition of waves and combinations of waves to create complex beat signals, which can be converted into individual waves, which can be then read and understood using a spectrometer, and give us peak positions based on the structure of a molecule. So the importance of superposition. So a complex waveform can be broken down into simple components by a mathematical operation called a Fourier transformation, which is what we just talked about. Jean Fourier was a French mathematician who lived from 1768 to 1830, and he demonstrated that any periodic function, regardless of complexity, can be described by a sum of simple sine or cosine terms of the original signal. So this combination or sum of the simple functions allows us to basically work backwards from a complex signal and produce individual signals from that. So the Fourier transform decomposes a function of time, a signal, into the frequencies that make it up. The Fourier transform is called the frequency domain representation. However, Fourier transform is tedious and time-consuming when done by hand, and so efficient computer programs are necessary. Remember, back in this time period, there weren't really any computers, there weren't any calculators, everything had to be done by hand. So to do a Fourier transform of even two waves that were pretty simple would have been time-consuming and difficult. But nowadays, it's pretty straightforward, and computers are very good at doing mathematics and mathematical operations, which means that it can be very efficiently done. So some of the properties of waves we've already encountered. We encountered how they move through a medium before, and how going from low density to high density resulted in the wavelength reducing, and also the velocity reducing, because the velocity was equal to the wavelength times the frequency. So if the frequency got less, or if the frequency stayed the same, but the wavelength decreased, then the velocity would also decrease. And so that was transmission of radiation from one medium to another. So the rate radiation propagates through a transparent substance is less than its velocity in a vacuum, and depends on the kinds and concentration of the different species present in the medium. Radiation must interact in some way with matter in its path. So it's going to be absorbed, or it's going to pass through, or something's going to happen. And so this is why certain types of radiation are very dangerous, and certain types of radiation are not, because some can interact with our biological tissue and some cannot. Frequency change is not observed. However, the interaction cannot involve a permanent energy transfer. Refractive index of a medium is one measure of its interaction with radiation and is defined as so, where n is the refractive index at a specific frequency I, which is equal to c, the speed of light. So that's 3.0 times 10 to the 8 meters per second, or 3.0 times 10 to the 10 centimeters per second. And then v is going to be the velocity of the radiation in the medium. So, well, c is the velocity in a vacuum, but since we're mostly talking about electromagnetic radiation, it's typically just the speed of light. And so this is kind of a schematic of what's happening. We've got incident beam, we've got it going through the medium, we've got transmitted beam. So some of the interactions that can happen are that it gets bent towards the normal or away from the normal. It can reduce in its wavelength, but that's only a temporary change, because remember that there's no permanent energy transfer here. So interactions of electromagnetic radiation. So we have physical interactions, which are not dependent on the characteristic of the wave of the electromagnetic radiation. And we have chemical interactions, which are dependent on the characteristics of the electromagnetic radiation. So the physical interactions are things like reflection, refraction, diffraction, scattering, and polarization, which we will talk about in detail. And the chemical interaction is sort of like the absorption process, which might happen during a UV-vis measurement. So the reflection of radiation, so that's off, like it's being reflected off of a surface. Refraction is the change of the angle of the propagation of the radiation. Diffraction then is kind of like the change of the angle after interaction of the wavelength of the wave. Scattering then is when a wave interacts with a particle or something and it just scatters off in lots of different directions. And then polarization is whenever we take unpolarized light which propagates in every direction, and turn it into light which only propagates in one direction. So refraction of a wave, so that's similar to what was happening whenever we saw the transmission through different media, but this time we're refracting it. So refraction of a wave, refraction is the change in direction of propagation of a wave due to a change in its transmission medium. So here we have medium 1, which might be air, and medium 2, which might be glass. And we have a normal here, which is at 90 degrees to the interface between these two media. And then we have an incident propagation direction, and that's got some angle theta 1. And then after it moves from the less dense into the more dense causes a bend in the direction of propagation towards the normal. So that gives us theta 2, which is more acute than theta 1. So the refraction of light in passing from less dense to a more dense medium results in bending it towards the normal. Less dense media to more dense means a bend towards the normal. So less dense, more dense, bend towards the normal. More dense to less dense means bending away from the normal. The extent of refraction is given by Snell's equation, where sine of theta 1, so this is theta 1 in medium 1, over sine of theta 2, which is theta 2 in medium 2, is equal to n2, which is the refractive index of medium 2, over n1, which is the refractive index of media 1, which is equal to the velocity in medium 2 over the velocity in medium 1. Reflection of radiation. So reflection occurs when radiation crosses an interface between media with different refractive indices. So here we have incident and reflected light. And it happens because the different media, so in air and the mirror, they have different refractive indices. And this means that they are going to cause a reflection. The reflection increases when the difference between the refractive indices is large. So if the refractive index of air is small and of the mirror is large, then we will get a lot of reflection. For radiation that enters an interface at right angles, reflected fraction is given as such. So the intensity of the reflected light over the initial incident intensity is equal to n2 minus n1 squared over, so the difference squared between the two refractive indices over the sum of the refractive indices squared. So where IR is reflected intensity, I0 is incident intensity, N1 and N2 are the refractive indices of the two media. You see a schematic here where incident and reflected light, the light is reflected because of the difference between the refractive indices of the medium here, which is probably air, and the medium here, which is a mirror of some sort. So laws of reflection. So we have different types of reflection. We have diffuse reflection, we have specular reflection, and we have incident light. So the laws of reflection. The incident ray, the reflected ray, and the normal to the reflection surface at the point of incidence lie in the same plane. So if the plane is the page, then all of the light must be in that same plane. So incident light and the reflections, so diffuse reflection, specular reflection, they're all in the plane of the page or the plane of the screen. And the point of incidence along here, along the mirror, is also in that plane. So the normal is 90 degrees to the incident or the interface. The reflected ray and the incident ray are on the opposite sides of the normal. So if the normal is here, the incident light is on one side, the reflected light is on the other side of the normal. Again, we have two types of reflection. We have specular reflection. So this is reflection of light from a smooth surface, a mirror-like surface. So you see here, this lake is giving specular reflection of the mountains because it is very still. And so we can get this beautiful photograph. Reflections on still water are an example of specular reflection. Diffuse reflection then, so diffuse reflection is light being reflected from a rough surface. So this retains the energy of the light because remember that these physical interactions do not cause light intensity or energy transfer. So the energy is retained, but the image is lost. So like if we had specular reflection off of a surface, we would see that it is brightened by the light, but it does not have the image that of the reflection. So a diffuse reflection of this would just show a bright lake. We would see a bright lake, but we would not see the image of the mountain. And that would be diffuse reflection. So here it happens whenever we have rough surfaces where there are many different angles, and this causes there to be sort of the internal scattering of the light. So it scatters off of these different interfaces quite randomly. Diffraction of radiation then is whenever we have parallel beams of radiation which are bent by a sharp barrier or through a narrow opening. So we can also see this for acoustic waves such as like the waves in the sea or musical waves that comes from a guitar or something like that. So here we have two different sets of parallel beams of radiation. So this is the wavelength, this is the distance between these blue lines. We have a wave generator here, a wave generator here. We have different apertures or openings. So this one is quite a wide opening, X to Y distance is large. And here the aperture is quite small, the X to Y distance is quite small. So XY, whenever we have XY being much greater than the wavelength, we don't actually really see a great deal of effect of diffraction on the waves. So you can see here, they're still pretty much parallel. Like there's a little bit of curvature at the edge of the interface, but by and large, the wavelength hasn't really changed. Well, the wavelength won't change, sorry, but the shape of the waves has not really changed much. Whereas here, whenever the XY distance is approximately equivalent to the wavelength distance, what we get is the bending of these parallel waves. So they're no longer parallel and they now are spherically diffracted. So they go from linear to spherical. Because like ultimately these things are not always necessarily in like just one flat plane. They're often three-dimensional. Scattering of radiation is whenever the electromagnetic radiation interacts with the small particles in the matter. And so this is a good way of finding out the size of the particles in the solution. So how this works is if the wavelength is somewhat similar to the diameter of the particle, as you can see here, the incoming beam, the particle, then what we will see is that there will be a certain degree of interference caused by this interaction, which will result in the scattering, sort of out of phase scattered beam, not having the same amplitude and really interacting destructively and becoming destroyed. So the scattering by molecules with sizes smaller than the radiation wavelength is called the Rayleigh scattering. Rayleigh scattering causes the blue color of the sky and is caused by the greater wavelengths scattering this, or caused by greater scattering of the shorter wavelengths of the visible spectrum. Scattering by large molecules can be different in different directions and is called Mie scattering. This is used to determine the size and shapes of colloids. So colloids are suspensions of droplets in a liquid. So milk is a typical colloid. Polarization of radiation then, so this is monochromatic radiation, has an equal distribution of planes centered on the beam path. So this is what a typical wave looks like. So it's propagates in all directions. I mean, I know their arrows only point in certain directions, but that's really just for clarity. It's actually pointing in all directions. It's kind of like a beam with individual vectors, which are infinitely thin, but encompass the whole space around the propagation direction vector. So the amplitude changes as we go along. So at high amplitude, you see the arrows are longer, and then it's at lower amplitudes, the arrows are thinner. But sometimes we don't want this in all directions, and we only want it in one direction. And so we have to remove all but one of these planes to create plane polarized light. The reason why we might want to polarize light is because sometimes, because molecules have different orientations in solution, they're not all facing the same direction. Sometimes we don't want to interact with all of the molecules, and we only want to interact with the molecules in a certain plane of the light so that we can do complex measurements, and we can ensure that we're not exciting molecules which are like perpendicular to the plane, or molecules which are offset from the plane. We want to create plane polarized light so we have more control over our experiment. So some interactions of light and matter, kind of a summary sheet here. So we have absorption and transmission. Here we have incident light to be measured, and we have transmitted light to be measured. So this is the idea that the incident light, some of it will be absorbed, and then whatever comes through the sample afterwards is the transmitted light. And so this has an intensity hopefully less than the absorption. So we have atomic absorption here, and we have a molecular absorption. Then we have absorption, then emission. So we're getting emitted light. So we're getting measurements like fluorescence measurements and phosphorescence measurements. We'll talk about like these kind of measurements as we go through. Scattering then, things like turbidimetry and nephelometry and Raman spectroscopy. Won't really talk about this so much in this course. Reflection, again, things like attenuated total reflection. This is a tool used in infrared spectroscopy, very important. Diffuse reflection IR. So this is also quite important in infrared spectroscopy, but again, we won't really talk about it here. You can even do reflection UV vis absorption measurements if you have a refracting sphere. Then emission measurements, so atomic emission, molecular emission, chemiluminescence. So we're measuring the emitted light here, but not necessarily the light stimulated emission. So like we don't necessarily have absorption and then emission. Sometimes we literally just measure the light which comes out from a sample, or the radiation which comes from a sample. So absorption of radiation is a very important property which we can utilize to make chemical measurement, or make physical measurements of our chemical systems to get things like concentrations. So the absorption of radiation occurs only if there is an interaction between the electromagnetic radiation and the material. So that means like the wavelengths or the energy of the electromagnetic radiation has to match some property of the material. So typically in things like UV vis measurements, that means that the energy of the light will have a intensity or a wavelength which matches one of the transitions inside of the molecule. So like a transition from a ground state to an excited state. And we'll see that as we go through. The energy of the electromagnetic radiation must exactly correspond to the energy of transition in the molecule. And so this is the general flow. So we have an incident intensity of light passes through the sample, which gives us the transmitted intensity, which is usually lower, assuming that some of it was absorbed. Now, it's not always absorbed. Typically in UV vis measurements, what we do is we kind of measure across the spectrum, so at different wavelengths, and not all of them absorb, and only some of them will absorb. So generally, the transmitted intensity is going to be less than the initial intensity, and this is because, but the amount to which that it is absorbed depends on the population and path length. So the population is important because the more molecules you have there, the higher the concentration, the more molecules there are that are capable of absorbing, or the more species that are capable of absorbing. And the path length, the longer the path length, the higher the chance there is that one of the species of interest is going to be in the beam of light. And so there are two reasons why these are important. So energy states then. So when a material, atoms, ions, or molecules changes its state from lower to higher energy, it absorbs an amount of energy exactly equal to the energy difference between those two states. So this is why it's important that the electromagnetic radiation that's going to be absorbed or interact with the sample should have some consistency with some of the internal properties of that material. And so this is one of those, especially in the terms of absorption. So the energy should match the energy difference between the two states. So usually this is the HOMO and LUMO in an absorption measurement of a molecular species. So the energy E1, the difference in the energies E1 and E0 is equal to H nu, where nu is the frequency, so this is our Planck's constant, is equal to Hc over lambda, where E1 is the energy of the higher state and E0 is the energy of the lower state, typically the excited state and the ground state. The various energy states are called electronic states. The lowest energy state of an atom or molecule is called the ground state. Higher energy states are termed excited states. We have the first excited state, which is the one after the ground state. We have the second excited state, which is higher in energy than the first, the third, the fourth, and so on. Typically, though, we'll only be talking about the first and maybe the second. Most species are ground state at room temperature. So actually, there's very few molecules in the excited states at room temperature. Most of it is in the ground state. So if we have two energy levels like so, we have the ground state E0 and the excited state E1. During the absorption process, we have an energy increase from the ground state to the excited state. The energy difference between these two states is given by H nu, where nu is the frequency, which can obviously be related to the wavelength. So the electromagnetic radiation should have a wavelength which represents the energy difference between these two states. Absorption of radiation is the process by which these molecules take in that energy and go from the ground state to the excited state. When radiation passes through a sample, certain frequencies may be selectively removed by absorption, a process in which electromagnetic energy is transferred to the atoms, ions, or molecules. Absorption promotes these particles from the ground state to one or more higher energy states, and the energy of the exciting photon must exactly match the energy difference between the ground state and one of the excited states of the absorbing species. Since these energy differences are unique for each species, a study of the frequencies of absorbed radiation provides a means of characterizing the constituents of a sample of matter. So this is the absorption process. So if we have some incident radiation with power 0, P0, so this is the incident radiation P0, and so that's going to interact with the sample, and the transmitted radiation, assuming that there's some wavelengths in here which represent an energy difference in the sample, so like a ground state to excited state type thing, the transmitted radiation will be lower in intensity than the incident radiation. And so it will go from the ground state to the first excited state and the second excited states. So this these energy differences will be E1 and E2 are going to be equal to H nu2 and E1 is going to be equal to H nu1. And these can be, since we know the frequency nu1, we can find the wavelength, and then that can be transposed onto a spectra like so. so that we can see the wavelengths which are absorbed. Radiation of incident radiant power P0 can be absorbed by the analyte, resulting in a transmitted beam of lower radiant power P. For absorption to occur, the energy of the incident beam must correspond to one of the energy differences in an atom or molecule. And this gives rise to an absorption spectrum, which is what we see here. So atomic absorption is the passage of polychromatic ultraviolet or visible radiation through a medium that consists of monatomic particles and results in the absorption of a few well-defined frequencies. Such spectra are very simple due to the small number of possible energy states for absorbing particles. So usually atomic spectra are basically line spectra. So they absorb at very specific wavelengths, and there's not really a lot of interference from other species, which might cause a broadening or a complex spectra to form. Molecular absorption, on the other hand, though, is much more complex, because what's happening here is you've got multiple different atoms bonded together or associated together in some manner that are able to dissipate energy or share energy between them. They have complex absorption and emission properties. Generally, they have an enormous number of possible energy states that are possible. And so these spectra are much more complex. And generally, atomic absorption spectra can be interpreted to find qualitative information about the species, what species is present, but molecular absorption generally is much harder to do with absorption. And so the energy E of a molecule is made up of three components. The energy is equal to the electronic plus the vibrational plus the rotational. We will predominantly only be talking about the electronic energy whenever we talk about absorption measurements. So that's going from the ground state to the excited state. But other types, these vibrational and rotational, also contribute to the overall energy of a particular state. The electronic energy, though, is a factor, a substantial order of magnitude greater than the energy of the vibrational, which is greater again than the rotational. So that's the order. Electronic is highest energy, vibrational next, and then rotational. Vibrational energy is kind of the movement of atoms in a bond, and rotational energy is the rotation of atoms in a bond. So here are some absorption spectra that we can look at. So we can see that absorption spectra can have different forms. We have here a sodium vapor. So this is an atomic absorption spectra. You can see the well-defined lines at different peak positions that are quite easy to interpret. Benzene vapor, so this is gas phase benzene. You can see it's also quite sharp, although much more complex. And that's caused by the structure of benzene. There are 6 carbons, 6 hydrogens. They're bonded together. Because they're an aromatic ring as well, they can share energy in the ring, and it creates a vast number of energy states compared to the atomic absorption. Then if we put the benzene in the liquid state, if we solve it in a solvent or something, depending on the interactions of the solvent, we get a broadening of the spectra. So benzene in hexane is a non-polar solvent, results in a spectrum which is still interpretable based on the peak positions, but it's a lot harder to interpret. And really, we would only use this kind of a spectrum for quantitative measurements, so things like concentrations. Then this biphenyl in hexane, the interactions here you can see cause a broad continuum, which is not really, you couldn't interpret this to say that biphenyl was in here, but we could definitely find out how much biphenyl was in there if we already knew that. So this could be useful for concentration. We just go to the maximum in this and then compare it across different concentrations and maybe set up a calibration curve or such. So absorption spectra can have different forms. Sharp peaks or smooth peaks are common. Spectra are affected by complexity of the sample, the physical state, the environment of the absorbing species. And the biggest difference is between atomic and molecular spectra. So you can see here the difference between here and here is larger than the difference between here and here. This is just a solvent effect. So the matrix that the sample is in, these are differences between atomic absorption spectra and molecular absorption spectra. Radiation emission then, so emission of radiation. So we have electromagnetic radiation is produced when excited particles, such as atoms, ions, or molecules, relax to the lower energy levels by giving up their excess energy as photons. Radiation from an excited source is characterized by means of an emission spectrum. So if X goes to X excited, so that's what this dot means, and then the excited state X will release energy in the form of light, which is often written as h nu. Remember, h nu is equal to E, where that relationship is Planck's relationship. So there are a number of different ways that we can do this excitation. We can bombard it with electrons. We can use an electron current AC spark. We can look at the heat of a flame and use the energy from that flame. We can use an arc or a furnace to produce UV vis or IR radiation. And then we can use a beam of electromagnetic radiation too. Photoluminescence then, so this is another form of measurement using electromagnetic radiation. So photoluminescence methods include fluorescence and phosphorescence. So these are different from emission, where emission just looks at the light that comes from a sample. Here, what we're doing is we're first exciting the sample, so we're getting an absorption event happening. And then after that, we're measuring the light which is emitted after the absorption, so during the relaxation process. So we have incident radiation here with a power P0, and that is incident on the sample. The sample then absorbs this light, and we could measure the absorbance if we wanted and look at the transmitted radiation here. And then the other side of the coin is that we measure the photoluminescence or the fluorescence that comes from the sample. So what's happening is that we're going from the ground state to the excited state, either the first or second, depends on the wavelengths or the energy of the incident radiation. And then after that, we're getting relaxations from the excited states down to the ground states, and that causes the emission of some light. So some light is emitted, and we're very capable of measuring that and seeing what wavelengths are emitted. Typically, the energy here is going to be less than that which was incident and absorbed, and that's because of things like heat transfer within the molecule, certain like collisions and things like that. So photoluminescence results from the absorption of electromagnetic radiation and then dissipation of the energy emission of radiation. Absorption can cause excitation of the analyte, so we go from the ground state to the excited state. And once excited, the excess energy can be lost by emission of a photon, like from here to here, here to here. And we can get, of course, a spectra based on that, because remember that the energy can be related to the wavelength via Planck's relationship. So emission occurs over all angles, and wavelengths emitted correspond to energy differences between the levels. So these wavelengths correspond to the energy differences between these levels. Emission spectra, like we also have similar types of emission spectra. We have line spectra, we have band spectra, and we have continuum spectra, and we'll see all of these shortly. So the relaxation processes occur, the lifetime of an atom or molecule excited by the absorption of radiation is brief, because there are several relaxation processes that permit its return to the ground state. Non-radiative relaxation. So non-radiative relaxation involves the loss of energy in a series of small steps, the excitation energy being converted to kinetic energy by collision with other molecules, and a minute increase in the temperature of the system results. So the emission spectra here, we can see all three in one. So we can see line spectra here and here and here and over here as well. These are all lines. We also have band spectra here. We can see a lot of overlapping lines. And then we have a continuum spectra, which is kind of like the background. So three types of spectra: continuum, line, and band. Line spectra are sharp, well-defined peaks. Band spectra are groups of lines that overlap and are not yet fully resolved. Continuum spectra cause an increase in the background spectrum. Atomic versus molecular emission spectra. So atomic spectra equal single lines, and molecular spectra equal band spectrum. So here we have atomic spectra single lines. So we have absorptions here and here. Because there are no bonds, there are no vibrations or rotations, and so any relaxations are simply down to the ground state or from the second to the first excited state. So the number of possibilities are much lower. So in this system of three energy levels, the ground, the first, and the second excited states, we have absorption, which can happen either from the ground to the first or the ground to the second excited state. Then after that, we can have relaxation from the first excited state down to the ground state. That will provide one wavelength in our spectra. And then we can have also the relaxation from the second down to the ground, which will be a second line in our spectra. And we could also have a weaker line or a slower intensity line from the second excited state down to the first excited state, which would then also relax down to the ground state eventually. But in the case of molecular spectra, we see over here in part B, we see that the absorption processes are the same, pretty much, but the emission processes are much different. And that's because in the ground state here, we have a bunch of other lines like 0, 1, 2, 3, 4. What are they? Those are the vibrational energy levels. And so the relaxation can happen down to there first, which means that it's possible for the wavelengths that we observe in the spectrometer to be those lines as opposed to the ones which go right down to the ground state here at the bottom. So fluorescence and phosphorescence relaxation. Fluorescence and phosphorescence are analytically important emission processes in which atoms or molecules are excited by absorption of a beam of electromagnetic radiation. Radiant emission then occurs as the excited species returns to the ground state. So there is some light produced by the spectrometer, maybe from a lamp, maybe from a laser, that is incident, so it hits the sample. The sample then absorbs certain wavelength frequencies from that, and then those absorbed frequencies cause a transition from the ground state to the excited states. Then the excited state molecules need to relax down to the ground state. And by relaxing down to the ground state, they release some energy. Some of it is heat, some of it is caused by collisions and kinetic energy, and some of it is emitted as light or electromagnetic radiation, which is what we pick up. Fluorescence is a fast process which occurs much more rapidly than phosphorescence. Fluorescence and phosphorescence are most easily observed at 90-degree angles to the excitation beam. So we have X, the species X becomes excited, then X releases light as H nu, where H nu is going to be less than the incident H nu. So here is a setup, a simple setup for emission spectroscopy, fluorescence or phosphorescence spectroscopy. We have incident intensity light is incident on the sample. That is going to cause an excitation from the ground to the excited state, which will then reduce the intensity of the transmitted beam. And then we pick up any light which is emitted by the detector at right angles to the incident beam. The reason why we do this is to try and avoid measuring the actual excitation beam. We don't want the light from here going into the detector because that can cause spurious data or can cause errors in our measurement. So luminescence then, so this is just the same thing. So incident radiation, incident on the sample, transmitted radiation is lower intensity than incident radiation. Then the luminescence or fluorescence happens to cause light to scatter in all directions. So we pick up some of those at 90 degrees to the incident beam. And then these are the internal processes on the energy level. So it goes from the ground state to the excited states. And then we have emission back down again. We can also have internal conversion events which don't actually release any energy. And so there are some complexities with regards to fluorescence measurements, but they're very useful in the sense that they have, there's a time delay before they're released. And so that can be used to understand things about the dynamics or the kind of chemical environment of the species. And then here we have a typical luminescence spectra. So fluorescence, we have two types of fluorescence. We have resonance fluorescence, which describes the process in which the emitted radiation is identical in frequency to the radiation employed for excitation. So that means like if we excite the sample and it absorbs at 400 nanometers, then if it has resonance fluorescence, then the energy or the wavelength of the light emitted would also be 400 nanometers. So resonance fluorescence is most commonly produced by atoms in the gaseous state that do not have vibrational energy states superimposed on electronic energy levels. Then non-resonance fluorescence is brought about by irradiation of molecules in solution or in the gaseous state. Absorption of radiation promotes the molecule into any of the several vibrational levels associated with the excited electronic levels. So this is caused by the vibrational levels, basically. Excited state lifetimes. So the lifetimes of these excited state vibrational states are only on the order of 10 to the minus 15 seconds. So they're very short-lived, much shorter lived than, for example, fluorescence lifetimes, which is much smaller than the lifetimes of the excited state electronic states, 10 to the minus 8. So that's kind of the order of fluorescence measurements. Vibrational relaxation typically occurs before electronic relaxation. And the energy of the emitted radiation is lower than that of the absorbed by an amount equal to the vibrational excitation energy. So excitation goes like this, the ground state. We have the excited state, ground state again. So excitation has the electron go from a lower energy state to a higher energy state, so from there to there. Then emission goes back from there to there. So phosphorescence occurs when an excited molecule relaxes to a metastable excited electronic state called the triplet state, which has an average lifetime of greater than 10 to the minus 5 seconds. So much longer, about 10 orders of magnitude longer. So here are some energy level diagrams for fluorescence. So infrared gives pure vibrational spectra because the energy of radiation is insufficient to cause electronic transitions. So these vibrational energy levels here, if we have IR radiation, the energy doesn't actually, it's not enough to go up to the excited state energy levels. So we can actually get very pure IR spectra because we only go up to the IR energy levels. We never go up to the excited state. I mean, it is possible to do those kind of measurements, but they're much more complicated and much more difficult. So the common ones are just staying in the ground state, ground electronic state, and exciting to different vibrational energy levels. Non-radiative relaxation involves the loss of energy in a series of small steps and the excitation energy being converted to kinetic energy by collision with other molecules and small increase in system energy. So non-radiative relaxation is caused by the collision of one molecule hitting another, and it can also be caused by transfer of energy from one molecule to another. And then resonance fluorescence, again, we talked about, is the idea that the emitted radiation is identical in frequency to the exciting radiation. So there's 4 major classes of the spectrochemical methods that we'll be looking at. So there's emission, which we've talked about, luminescence, which we've also talked about, scattering and absorption. So they have what we measure is the emitted radiant power, the luminescent power, the scattered power, and the incident and the transmitted for absorption. So the methods involved, so for emission, it's atomic emission. For luminescence, it's atomic and molecular fluorescence, phosphorescence, and chemiluminescence. So chemiluminescence comes about by chemical reactions or association of different molecules. Raman scattering, turbimetry, and particle sizing are used for scattering. So that's like a zetasizer, which might look into the size of nanoparticles suspended in a liquid. Then absorption is atomic and molecular absorption, of course. And here are their concentration relationships. And so what you should notice is that in the first 3, emission, luminescence, and scattering, the power of the radiant power is proportional to the concentration by some constant K, which is system dependent, but it is more or less proportional. However, with absorption, it is no longer directly proportional. And so we require 2 measurements here. We require one before and one after the sample. So emission, luminescence, and scattering methods, the power of the radiation emitted by an analyte after excitation is usually directly proportional to the concentration of the constant, or proportional to the analyte concentration C. It says usually there because we'll learn about some things later in the Beer-Lambert law, which will make it that there are certain conditions for non-proportionality. Whenever we get to those ranges, so usually it's due to too high a concentration or too low a concentration of our analyte. And so that causes non-linearity in our calibration curves and in the Beer-Lambert relationship, which means that they're no longer proportional. So we have to stick within a certain concentration range. Then quantitative absorption methods require 2 power measurements, one before the sample and one after. Okay. So absorption methods, so we have quantitative absorption methods require 2 power measurements, as we said before. There's one before a beam has passed through the medium that contains the analyte, so that has incident radiant power P0, and the other after the sample, which has a radiant power of P. These 2 terms, which are widely used in absorption spectrometry and are related to the ratio of P0 and P, are called transmittance and absorbance. Spectrophotometry is a method to measure how much a chemical substance absorbs light by measuring the intensity of light as a beam of light passes through the sample solution. The basic principle is that each compound absorbs or transmits light over a certain range of wavelength. Transmittance, the transmittance T of the medium is the fraction of incident radiation transmitted by the medium. So transmittance is equal to P, the radiant power after the sample, divided by P0, the radiant power before it enters the sample is the incident radiant power. And so it should have a value from 0 to 1. So 1 would indicate that none of the light had been absorbed. Where P0 is the incident power of the beam and P is the power of the beam after absorbed by the sample. Transmittance is often expressed as a percentage. So remember, in the case of light, we cannot create more light than we had initially. So if you were doing a problem or something based on transmittance and you got a value more than 1, there's probably something gone wrong. Absorbance then, the absorbance A of a medium is defined by the equation A is equal to minus log to the base 10 of T, which is equal to minus log the base 10 of P over P0. So we just like substitute this into here. And then that's equal to log of P0 over P, because like one of the properties of logs is that you can flip the denominator and the numerator. And then you just change the sign in front of the log, which is equal to the log of 1 over T, the transmittance. So absorption methods. So the power is higher before the sample. So here, it should be higher before the sample than after the sample so that some of it can be absorbed by the solution of concentration C. And T, of course, is equal to P over P0, and A is equal to log of P0 over P. So it's all based on this power, incident power and transmitted power. Okay, so the Beer-Lambert law is fundamental to all of this. For monochromatic radiation, absorbance is directly proportional to the path length B through the medium and the concentration C of the absorbing species. And these relationships are given by A is equal to ABC, where A is the proportionality constant called the absorptivity and is actually usually given the letter epsilon. The magnitude of A in this sense will clearly depend upon the units used for B and C. So B is the path length typically, so that's usually in centimeters, and C is the concentration, usually in moles per liter. So for solutions of an absorbing species, B is often given in terms of centimeters and C in grams per liter. Okay. This is not for the molar absorptivity. This is just for the, okay. So yeah, there's another version, which we'll see later, which is the more common version. But this is the basis of it, the traditional version. So absorptivity then has units of liters per gram per centimeter when the concentration is expressed in moles per liter and the cell length is in centimeters. The absorptivity is called the molar absorptivity. So this is where A becomes epsilon. It's given the spectral symbol epsilon here. This is the molar absorptivity or the molar extinction coefficient. Thus, when B is in centimeters, so this is the path length, and C is in moles per liter, A is equal to epsilon BC, where epsilon has the units of liters per gram per centimeter. The above equations are expressions of the Beer-Lambert law, which serves as the basis for quantitative analysis by both atomic and molecular absorption measurements. This is a very important law. A is equal to epsilon BC. But you can't have absorption without having a molecule or something like that. So here, as we come towards the end, here's a typical absorption setup. We have some sort of light source. Then we have a filter to control the intensity of that light source after it's been parallelized by the lens. We have a shutter to turn on and off the lamp. We have a diaphragm, which can set the transmittance to 100%. Then we have a sample cell and we have a solvent cell. So we need to always have a blank and a sample. So usually they're set up parallel. In most modern spectrometers, there's like the ability to shine the light on both simultaneously. But in some older ones, you have to manually like shunt them in and out. There's like a little lever which moves the position of the two cells. And then there's some photoelectric device which measures the intensity of the incident or the transmitted light. And then, of course, that can be converted by a transducer into an electrical signal. Then that electrical signal could be read by the computer or by the step motor or whatever it happens to be to give us a readout, which we can understand. So the transmittance here is 74.3%, which means that this transmitted beam is 74.3% of the original incident beam. So what 25.7% of the light has been absorbed. So the photoelectric device is a transducer that converts non-electrical signals to electrical signals. Remember that. Remember that from the first session where electrical signals are what we're actually measuring. So let's check comprehension. So I encourage you to try and do this yourself. Pause for a few seconds if you need to do this. We're going to be using the Beer-Lambert law here. We're just doing an absorption measurement. So we just went back and look at the previous slides if you need to get the equation. A is epsilon BC. Again, pause if you need more time. Otherwise, we'll just continue on and we'll talk about the answer. Again, pause if you need more time. Perfectly fine to take your time. Okay, we're going to share the answer now. So I recall from the previous slides that the absorptivity or the absorption is equal to the molar absorptivity or the molar extinction coefficient times the path length times the concentration. We have here the absorbance in atomic units. We have here the path length and we have the concentration. So we then need to rearrange this equation to get it in terms of the molar absorptivity, which is what we're asked to find. We're asked to find absorptivity of a sample if its absorbance is 1.2 atomic units, path length 1 centimeter, and concentration 0.8 moles per liter. So we plug in our values here, and we see that we get a value of, well, just put it in the calculator, get it out, 1.5 liters per gram per centimeter. And that will do us for the first part of this. Thank you for watching.